Now, I wanted to do a couple of examples where we apply these techniques but involve a little bit of calculus. This is a calculus-based physics course, so we might as well see how calculus can be applied in these kinds of motion problems. Now, one example of a place where calculus is necessary is when the acceleration is not constant. You know, if the acceleration is constant, we have our kinematics equations, but how do you handle a situation where the acceleration is not constant? Let's look at an example where that's true and see how we would handle it. So here we have a simple problem. The acceleration of a body is given by A equal to 7.0 meters per second cubed times t. Now, note the units. We know that for an acceleration, the units need to be something like meters over second squared, a distance over a time squared. This is times t, which is going to have seconds. It'll cancel with one of those seconds in the units here, and that'll leave us with meters per second squared as the total units of this term. So our units do make sense, and I just wanted to point that out. Now, the question is, given this acceleration, and hopefully it's obvious that this acceleration is not constant because it varies with time. At 1 second it's 7, at 2 seconds it's 14, etc. So the acceleration is increasing with time. That means the kinematics equations don't work. You can't use them. So how do we handle this kind of a situation? So let's look at the actual problem is asking for. It says if it starts from rest, so we know that v0 is 0, what will its displacement and velocity be after 2 seconds? Okay, so we're going to basically do what we did with the derivation of the kinematics equations, only the acceleration is not constant, so we'll have to see how that changes things. So we'll start here. We have dv over dt is equal to a, our acceleration. And of course we'll be able to plug in 7 meters per second cubed times t for our a. But before we do that, let's see what we're going to do. We're going to do our separation of variables again. So I'm going to take this dt and I'm just going to move it over onto this side of the equation. It's almost like treating it as a fraction, and I'm just multiplying it across. And so basically I'm solving here for dt. Now I've got dv, which is a differential, is equal to a dt. So to solve for that, we're just going to integrate over both sides. And so if I do that, I get dv, which is going to go from rest, velocity equals to 0, to some final velocity, is equal to a times dt. Now, normally a is a constant, and we'd be able to pull it out of the integral. But since a has a time dependence, you cannot pull it out of the integral. And of course, the time is going to go from some initial time 0 to some final time t sub f, and so those are the limits of the time integral. So I'm going to just plug in my value for a. My value for a is 7 meters per second cubed t. That's what my a was. And then I'm going to integrate it over dt. And that's going to be the next step. Now, if I look at this portion here, this 7 meters per second cubed, that is a constant, and I can pull that outside the integral. And so my actual integral is going to be something of the form t dt times that constant out front, and that's just going to be t squared over 2 from 0 to the final time t sub f. And so that's what that integral is going to give us. And of course it'll be multiplied by that constant, that 7.0 meters per second cubed. That's the constant that gets out in front. And so this is the result of this integral here. Now the integral here, dv, the integral of dv is just v, and that's going to go from v final to 0, and so we can say that v final minus 0 is equal to this term over here, which is going to go from t final to 0. So we can get rid of those zeros, and what we end up with is that our velocity is going to be 3.5, that's 7 divided by 2, meters per second cubed times t squared. And we wanted to know what the velocity was at 2 seconds. I just plug it in. And so when I plug that in, that gives me 4 times 3.5, and that gives me 14 meters per second. So I've got Seconds cubed here is going to cancel with the seconds squared, leaving meters per second. That's what we would expect for a velocity. And so at t equals to 2 seconds, we get a velocity of 14 meters per second. Okay, the next thing we want to do is we want to find the displacement, how far it moves. And in order to do that, we can integrate the velocity function. We know that v is equal to dx dt. And so again, I can do my separation of variables. I can take this dt and I can move it over. So I can take this dt here and just move it over there. And so I get d of x of t is equal to v of t dt. And then I can just simply integrate both sides. So that's what I have down here at the bottom, and I've plugged in my limits. My dx integral is going from some initial position 0 to some final position x sub f. My time integral is going from some 0 value to some tf. And so what is my v of t? Well, that's just what I found up here. This is my velocity as a function of time, and it is 3.5 meters per second cubed t squared. So that's what I've plugged in for v. And now I just have to do these integrals. So the integral on the left is just dx from 0 to x final, and that gives you, well, that integral is equal to, if I wanted to write it all out, I would say that's x from 0 to xf, which is of course what I have here, x final minus 0, that gives me x final. And then my time integral is 3.5 meters per second cubed t squared dt. Well, what's the integral of t squared dt? That's just t cubed over 3. That's the integral. The constant part will of course come outside the integral, but when you end up with all of that, you get, doing this integral, you get 3.5 meters per second cubed times t cubed all over 3, and that's from t equal to 0 to t equal to 2.00 seconds. Plug that time into there, multiply everything out, and you get the final position is equal to 9.33 meters. And so this is how you can apply it. And, you know, these could be any function of time. It could be time to the 1/2 power, time to the 5th power. It could be to the exponential, e to the minus t. It could be any time function that you want. You just do the calculus and solve for the velocity and solve for the position. Now, this is a problem I found somewhere on the internet. I'm not exactly sure where it came from, but the page that I saw it on didn't actually have it worked out correctly. And so I decided to play around with it, and I really like this problem. It's kind of clever, and it's a problem that does involve using a little bit of calculus, but not in a usual way. And so I think this is a good calculus review as well as a really interesting physics problem. So let's go through it real quick. It says a lifeguard, and this would be our lifeguard over here at the bottom of the screen. He's standing at the side of a swimming pool and he sees a child in distress. This would be the child that's going to die drowning unless the lifeguard can get there in time. And so the lifeguard runs toward the child. He runs with an average speed of 4 meters per second along the pool's edge for some distance x. And so the lifeguard goes along the x, and then at some point he jumps into the pool and swims in a straight line towards the child. But his swimming speed is much slower than his running speed, and so he swims only at 1.5 meters per second. And so the problem is, find an expression for the time it takes for the lifeguard to reach the child. And then 2, determine the value of x, that's the distance run along the pool, that will enable the lifeguard to reach the child in the shortest possible time. Now, the way this works is if the lifeguard jumped straight into the pool and tried to go straight, that's at the slowest speed. And so he's not going to get there as fast as he might otherwise if he ran a little bit first to get closer before he jumped in the pool. But if he runs too far, if he tries to run all the way over here and then go that way, that could be a longer time too. We want to find what's the optimum distance x so that he runs this far along the x and he swims that far towards the child. What value of x will give the shortest amount of time? And so in order to do that, we need to find an expression for the time it takes the lifeguard to reach the child in the first place. Now, this part doesn't actually require any calculus, it just requires a little bit of geometry. So we're given some parameters in the problem that the distance from the child to the edge of the pool is 8 meters, and the distance, that is the distance that the x distance that the child is away from the lifeguard is 10 meters, and so we have this horizontal distance and this vertical distance given in the problem. And so we know that the lifeguard runs some distance x, and so he goes some distance x along the edge of the pool. This distance from here to here is still going to be 8 meters. The remaining distance, that distance there, if from here to here is d and from here to here is x, this distance is d minus x. And we need that because we want this triangle, this 8 meters here, this will be d minus x, and that'll enable us to get that length by the Pythagorean theorem. And so, in general, we want the time it's going to take the lifeguard to reach the child. And so that's going to be the time he spends running plus the time he spends swimming. So time running plus time swimming. Now, the time he spends running is going to be just x over v running. And how do we know that? Because we know our kinematics equation. The lifeguard is not accelerating. He's running at a constant rate. So that means we can write down that in general that the distance that he travels x is going to be vt, velocity times time. And if we solve for the time, that's just going to be x over velocity. And that's what we have here. So the time he spends running is going to be the distance x divided by the velocity with which he is running. And the time swimming is going to be this distance, which is given by the Pythagorean theorem, 8 squared, so this is that side squared, times d minus x squared, where d is 10, so I've plugged there, 10 minus x squared, and all of this is squared, all under the square root. That's the length of this side of the triangle by the Pythagorean theorem. And so when you plug in all the numbers for the velocity that the person has running and the velocity that the person has swimming, you get t is equal to x over 4 meters per second squared, 4 meters per second, plus 8 meters quantity squared plus 10 meters minus x quantity squared, all under the radical, then divided by 1.5 meters per second. And so if you plug in different x values, that will tell you what the total time is and how it changed. So I could literally plug in x equals to 2 meters here, x equals to 2 meters there, and see what's the time. I could plug in x equal to 6 meters here, x equal to 6 meters there, and see, is that time bigger or smaller? We want the smallest possible time. Now you can't possibly plug in every possible time. You could plug in a bunch and maybe guess get pretty close, but we want to know what the exactly smallest possible time is. And in order to do that, we need to apply a little bit of calculus. This is an example of what's called a related rate problem. And I know you did a bunch of those in calculus, and I'm sure you all love them. They're so much fun. But that's basically what we're going to have to do here. But before we do that, actually, we can solve this another way without even applying any calculus at all. Because we can simply graph this function. Normally we graph x versus t, but we could actually graph t versus x. And so you can see this is exactly what I have done. I have plotted a function, this function here. I just plotted t versus x. Now, of course, when you're plotting this, the square root means take it to the 1/2 power. So everything in brackets is to the 1/2 power. I've got x over 4, the distance swimming, which was given by that Pythagorean theorem, that divided by 1.5. And I just plotted t for different values of x. And what you can see is that as the x increases, that the time decreases, and then there's some minimum value, and then the time increases again. Now, where is it a minimum? It looks to me to be a minimum around here, somewhere between 6 and 7. It's hard to say exactly, but it looks like somewhere between 6 and 7 is where the minimum is. And so, if you're a lifeguard, that might be good enough. I need to run about 6 meters, and then I need to jump in the pool and swim to the kid. But let's see if we can get the actual optimum value. So, in order to find the x that's going to give the minimum value to reach the child, we're going to take the derivative of t with respect to x. And then we're going to set that equal to 0. Because we had that function, and so we had a plot of t versus x on the other slide. And so we had this function like that, t versus x, and we know there's a minimum. If I want to find that minimum, I simply take the derivative of t with respect to x and set it equal to 0. And that'll give me the critical point corresponding to that minimum. Now, technically, it could give a minimum, it could give a maximum, or it could give a point of inflection. That's what that derivative being set equal to 0 does. And so if we wanted to really prove that it would be a minimum, we would need to do the second derivative test. And taking the second derivative of that function and figuring out when it's positive and negative, it doesn't sound like a lot of fun. But we already know that our answer has to be around 6 or 7 because we cheated by making the graph. And so if we have multiple solutions and one of them is around 6 or 7, that's going to be the one that we want. And the other would either correspond, I don't think this is going to turn around up here, but there's probably a point of inflection or something maybe elsewhere that we don't have to worry about, because we know if we get a solution that's near where our minimum is on our graph, that's good enough for government work. So let's take the derivative. Here's the function we have. We've got t is x over 4 plus 8 squared plus 10 minus x all squared, and then that's in the bracket to the 1/2 power divided by 1.5 meters per second. That is the time as a function of position x. And then we just take the derivative of t with respect to x, take the derivative of this whole function with respect to x, and set it equal to 0. And that's going to give us the minimum time. And so you take the derivative of x, you get 1, so that leaves me 1 over 4 minus, you take the derivative of this, the 1/2 comes down, you take the derivative of the inside, this power gets decreased so it becomes negative 1/2. You'll see that in the denominator here. This divided by the brackets to the 1/2 power, that's really the brackets to the minus 1/2 from when I took the derivative. And so basically, you just take the derivative of this. This is the first term, this is the derivative of the second term, and then you set it equal to 0. Now, this is 10 minus x. There's divided by 1.5 here. So I went ahead and did that division, and that gives us 10 divided by 1.5 gives us 6.67. 1 divided by 0.5 gives us 0.667. And notice the units here, that's going to be seconds, and this is seconds per meter times x, which is going to give us seconds as our total unit, which is what we are looking for. And then we have this guy over here, and we can do some messy algebra because we have to solve for x. And so what I would do is I would basically cross multiply in order to simplify this. So I'm going to take my 1 times the square root and then my 4 times this guy, and when I cross multiply I get this. And so this is a simplified expression, but it's still not all the way done. In order to keep going, we've got this under the radical is equal to that. We're going to square both sides. And so that'll get rid of that square root, and what we're left with is a very messy quadratic equation. Messy, tedious. Aren't you glad I did the work for you? So if you multiply all this together, you end up with this on the left side and this on the right side, and then you want to move everything over to the left-hand side, or rather move everything over to the side such that the squared term is positive so that we can apply the quadratic formula. and we end up with 6.12x squared plus 1.22.4 meters x plus 547.8 meters squared equals to 0. And when we solve for that with the quadratic equation, we get two solutions. X equals 6.76 and x equals 13.23. And wait a minute, that's between 6 and 7, so that must be our solution. And so from the graph, we can pick the right root. This must be a point of inflection. This is a minimum, and that corresponds to the minimum time for finding the, or rather, reaching the child. And so the runner wants to run 6.76 meters vertically and then go off diagonally swimming, and that will give him the minimum amount of time in which he can have the best chance of saving the child's life.